Here's just a very quick introduction to Huygens Principle and dispersion, without a whole lot of details. So first of all, Huygens Principle basically tells us that the information in a wave, you don't need the whole wave to know everything about the wave, because the wave propagates. And the basic idea is, if I make a wave, say in this example I'm making a sine wave by moving something up and down, if I look over here and see what the sine wave is doing, I know what the sine wave is going to continue to do. I don't need to know what the source is doing here or where the source is. If I know what's happening here, I know what's happening downstream, and I can reconstruct what happens downstream just by watching what happens here. Now when you take Physics 318, you'll learn more about Huygens Principle, and you'll learn that Huygens Principle doesn't strictly apply in 1 and 2 dimensions, but we're going to do 1 and 2 dimensional examples here anyway. It's close enough. It applies well enough that you can get the idea. Alright? So I've got this string, it's oscillating because I'm wiggling it at some point. If I watch what happens at one point, and then I take the string and wiggle it that way over here, so I watch what the string is doing here at this green point, if instead of actually making the wave here, if I just wiggle my string up and down here at the green point, you can see that the wave I produce by wiggling the green point is the same wave I produce by wiggling here at the black point downstream. Now upstream, all bets are off. But downstream I reproduce the same wave. Now if I have a point that's emitting spherical waves, Huygens construction tells me I can think of, this wave out here as coming from this point, or I can think of it as a bunch of other points on a surface emitting to generate that wave. For example, if I take a bunch of points on the surface of this wave and I say, let's pretend like this point is not generating the wave. Let's imagine instead that I have some little oscillators oscillating up and down here. Each of them makes a spherical wave. I add all the spherical waves together, and they cancel each other out here, but they add constructively here, and you end up reproducing the next ring of our wave. So the idea is, if I have points all around the sphere that are oscillating the same way they would oscillate if a wave from the center was coming, those points oscillating will generate the same wave out here we would have gotten if we had a point in the middle moving. So the point is, all the information about this wave and its future is contained on the surface of this shell right here. Alright, so another way of saying that is that this three-dimensional wave can be described completely just by knowing what the wave does on a two-dimensional surface. This is known as the holographic principle because it's the same principle that makes holograms work. So Huygens construction helps us understand how holograms work. Alright, and then I can, from these same points, I can generate the next wavefront, and so forth. Now imagine I have a wave, a plane wave. Alright, I'm going to take a bunch of points on that plane wave, add those together, and they make plane waves. Alright, so the point is, if I figure out what a wave is doing on some surface, and I imitate what the wave's doing just in that surface, what will happen downstream is exactly what I would have gotten from the original wave. Alright? So here's an example. Here's a plane wave. I just calculated, the displacement, the height as a function of time for a two-dimensional wave, plane wave. Alright? Now, if I have just one source wiggling up and down here, it makes a spherical wave, right? Or a two-dimensional analog of a spherical wave. Alright? If I add two sources together, four sources every quarter wavelength, as I add more and more sources together oscillating, I start to build something that no longer looks like a spherical wave, but it looks like a plane wave. And that's the idea of Huygens construction. Now let's talk about dispersion. So dispersion is basically, it refers to the fact that as a wave travels through a medium, different frequencies of sine waves will travel at different velocities. We talked a little bit about this in the wave section. Alright? So why does dispersion occur? For example, I send light into glass, and red light and blue light travel at different velocities. The index of refraction is different for red light and blue light. Well, why is that? And it's different from what you get in a vacuum. Alright, so the basic idea is this. Imagine I've got a little electron in the solid, and that, in my glass, along comes a light wave. That light wave makes the electron move up and down. But because I mean, this electron, you can kind of think of it as a mass on a spring. I've got this electron and it's bound to a nucleus, for example, or bound to some ion in the crystal. And so as I wiggle it, there's a restoring force, and so there's certain resonance frequencies that my electron wants to wiggle at. If I'm driving not exactly on resonance, it will oscillate out of phase with the drive. So the blue line here represents the light wave coming in, and the red is my electron moving up and down, and it moves up and down a little bit out of phase with the blue light. All right? Okay, so what happens is the blue light, well, I guess in this case it is exactly in phase. We're going to see what happens when it's not exactly in phase. As you change the wavelength, the phase changes, and how big your electron responds changes. What happens downstream is, all right, the blue, the original light, gets smaller because the electron has absorbed some light, but because the electron is moving, it emits light, and we add them together and we get the black wave, and we say, oh, okay, this electron and the way I've drawn it right here, it's oscillating with the right phase in order to do nothing to the wave, basically. But if I change that phase a little bit, now watch, the electron's oscillating a little bit out of phase. So we take away some of the blue light, we add in some of the red light, and when we add them together, we get the black one right here. All right, and notice that the black line, its peak trails the blue one a little bit. So every time we pass an electron, the phase of the light gets pushed back a little bit because we absorb some of the driving light and then coherently emit because the electron is wiggling in our semi-classical picture. But because it emits out of phase, it changes. When we add them together, we get something which is moved back a little bit in phase. All right, now every time we go past an electron, we get moved back a little bit more, so the more glass we go through, the further back we get pushed, and we interpret that as saying, oh, well, the velocity of that sine wave is slower than it would have been in vacuum. All right, so, but how much phase shift you get, how much absorption and rescattering you get, it depends on the wavelength. It depends on how close that wavelength is to the resonances in the electrons. All right? Now, most transparent things tend to have resonances at very short wavelengths, shorter than visible light. So visible light, the wave tends to get pushed back. All right? And so we have indices of refraction that are greater than 1. If you start shooting X-rays at materials, you can find materials that have, for X-rays, an index of refraction which is lower than 1, which means that the speed of the light is faster for that particular wavelength than it is in vacuum. Now, if you'll recall back when we talked about waves, we talked about group and phase velocity when we talked about dispersion. So the phase velocity is just the velocity of the wiggles. It's not really the velocity that the energy travels at. So it's okay to have a speed of light in a material that's faster than the speed of light in vacuum, even though we don't normally experience that with visible light. All right, because like individual pulses will travel slower than that. All right, but it's possible for the phase speed to be bigger or less than. For blue light, you tend to have a bigger index of refraction than for red light because you're closer to resonance and you get a bigger effect. So now that we're talking about different wavelengths, let me show you the electromagnetic spectrum. It turns out that visible light is just an oscillating electromagnetic wave. It's basically the same phenomena as X-rays and infrared light and radio waves and microwaves. They're all really the same thing. It's just that you have oscillations at different frequencies. Now, when they interact with materials, they behave very differently because materials have certain resonances, right? So X-rays tend to go through things that visible light won't. It's the same phenomena, but because the X-rays are oscillating at a different frequency, they don't interact the same way with matter, but it's the same phenomena. So really short wavelengths have really high frequencies. So short wavelength, high frequency would kind of in the extreme limit, we get what we call gamma rays, X-rays, ultraviolet, and then we have the visible spectrum. Blue has the shortest wavelength and red has the longest, but then once we get out of the visible, we have infrared, then microwaves and radio waves, and so forth. All right, so it's all the same phenomena. Just to give you a feel for what some different wavelengths are that you might recognize in real life, most of the things that we see with our eyes are not a pure sine wave. They're not a pure frequency. They're a mixture of different frequencies that our eyes interprets. But if you look at different lasers that have very specific wavelengths, you can kind of see, you know, what wavelength goes with what color. Probably most of you have seen a 405, a violet laser pointer, right? These purpley colored laser pointers, that's 4 or 5 nanometers. Now you have to be careful because when you shine one of them, well, you have to be careful because they, first of all, this isn't what I was going to say, but since I said the word careful, I might as well give you a laser safety tip here. This is, your eye does not have a lot of response at 4 or 5 nanometers. So what may look like a very weak beam is actually a significantly brighter beam. And a lot of the 4 or 5 nanometer laser pointers that you can buy are actually a lot brighter than they say they are because, you know, they want to pretend like they're less than 5 milliwatts and so that they're safe to be a laser pointer and they can sell them legally. But if you actually had one that was 5 milliwatts, it would look really dim because your eye doesn't have much response there. So they tend to be a lot brighter. But anyway, you need to be careful about that, but you also need to be careful when you try and interpret the color because they tend to make things fluoresce. A lot of things have resonances that can absorb that light and emit a different color. So if you shine one of these purple laser pointers at a piece of paper, you tend to get blue light. But if you shine it like on a white painted wall, for example, typically it looks more purple. That's the real color. So that color of purple you see when you shine a purple laser pointer on the wall, that's 4 or 5 nanometers. All right. In my lab, we have a laser at 423 nanometers, or we used to. It doesn't work anymore. We don't do that experiment anymore. But it's kind of a violet blue color, 423 nanometers. Argon ion lasers can put out several different laser lines. One is at 488 nanometers, and it makes a very bright baby bluish kind of blue. All right, so that's 488 nanometers. It also puts out a line at 514, which is a beautiful forest green. The green laser pointers you've seen, kind of they're a bright green color, that's 532 nanometers. All right? I've worked with dye lasers, and one wavelength I used a lot was the sodium laser cooling line at 589 nanometers. That's an orangey yellow, so 589 is orangey yellow. 633 nanometers is the wavelength of a helium neon laser. You've probably seen one. I've worked with a diode laser doing some experiments at 657 nanometers. All right, so 630 to 650, 660, that range is kind of where you find typical red laser pointers. So if you pick up a red laser pointer, it's probably anywhere in here. And notice that you really can't tell the difference between the color of different red laser pointers, even though, whoops, one of them's maybe at 630 and one maybe at 660. So your eye kind of, once you get to this point, everything looks red. We have a laser in my lab at 922 nanometers. That is technically an invisible laser. It is an infrared laser. But your eye has a little bit of sensitivity out there. It looks like a red laser pointer. In fact, it's a 1.5 watt laser, not a 5 milliwatt laser pointer, but it looks like a laser pointer because the eye's response is so low, but it just looks red. All right, so there's some colors that you can think about.